Hello everyone. I wanted to create this video to explain chair conformations. I realized it was a little hectic in class yesterday, so I hope this video will help with your understanding. So the first thing I want to cover is, why do we even want a chair conformation in the first place? Well, let's start by exploring what happens if we had a planar cyclohexane. Okay, so this is in the plane of the board. And remember, in this bond line notation, that there are hydrogens attached to the carbons in order to create the 4 bonds. So we have one hydrogen here, one hydrogen here. And again, it's on all those carbons, but I don't want to draw that in right now. So if we had a planar cyclohexane, the bond angle right here would be 120 degrees. But we know that this carbon is sp3 hybridized, which means that it wants to go into a tetrahedral shape. Now, if we want to go into this tetrahedral shape, we'd have a bond angle of 109.5. So right now we have these bonds at 120, and they're wanting to go back to this 109.5. So there's ring strain. There's strain in those bonds that are wanting to go back to that tetrahedral angle. And so therefore, we're going to create the chair conformation to obtain those 109.5 degree angles. So if we're in this conformation, these angles right here are 109.5 between all the carbon-carbon atoms. Even if my drawing is slightly off, it's 109.5 degrees in the carbon atoms. So that's why we obtain this chair conformation here instead of having it planar. So now that we generally understand why we have this chair conformation, again, there's no ring strain, we're able to obtain the tetrahedral angles of 109.5, I'm going to explain how we label this with the axial and the equatorial parts. So first we're going to start with axial. Now the way that I like to think about axial is, you see how these two bonds right here are coming down and they're forming a point. Well, this point is facing downwards. So we're going to have an axial bond, which is directly pointing downwards. Now these two right here, they come up and they're kind of forming an arrow pointing upwards. So we're going to have the axial bond going up like that. Now we can go around the molecule and we can create all of these axial bonds. So here, this one's slightly pointing down, slightly pointing up, so we create up axial, slightly pointing down, so we have down axial, and then we're pointing up again. Now, we also have an equatorial position. But before we get into that, I also want to create this invisible plane. So this invisible plane right here is perpendicular to the axial location. So this plane goes right like this, okay? Again, perpendicular, and we're going to draw this plane for all of the carbons. Again, perpendicular to the axial position. Okay? So now what's going to happen is we're going to place the equatorial bonds onto this compound right here. So equatorial are going to be on the other side of this plane, but they're going to be slightly above. So if this axial is facing down below the plane, the equatorial is on the other side, slightly above, but it's pointing out. It's on the outer side of the cyclohexane molecule. Now, this also maintains our degree angle of 109.5. So in this case over here, we have an axial that's pointing up. Remember, we had that because this bond looks like it's pointing upward. So we have an axial that's pointing up, and now we have an equatorial on the other side of this plane that's to the side, but it's slightly pointing down. This one, we have an axial that's below, so we're going to put it up. We're going to continue following along this trend the entirety of the molecule. So we have our green axials, which are again pointing straight up or straight down, and our equatorials are opposite pointing of the axial on that carbon, but it's just slightly above the plane. So that right there is how we create our axial and equatorial constituents on each carbon. Again, we are maintaining with this a 109.5 degree bond between the axial and equatorial, and we're maintaining the 109.5 between the axial and the carbons and the other bonds that are occurring in this plane. So in order to understand cis-trans, it's very important to remember these imaginary planes that we have here. So I'm going to redraw this again. Remember this picture right here. Actually, I'll redraw right next to the side. So I'm going to draw this same structure. So we have axial, equatorial, axial. I'm just going to go through real quick and draw the axials, because those are the easiest for me to draw first. Then I go back through and I draw the equatorials. So remember that there are this imaginary plane that is perpendicular to the axial position. Okay? So let's start with this axial position here. Okay? We're going to call this the red axial. Now, if we were looking at this carbon here, this equatorial position is actually going to be on the same side. It's on the same side of the plane. It's on the upper side of the plane. So this red is cis to this axial position. So this equatorial position above this invisible plane, this plane right here, is on the upside, is on the same side as this axial position. So if we're looking at this carbon here, comparing it to this carbon here, this axial is going to be on the upper side compared to this equatorial, which is on the upper side of this carbon. So we can go around the molecule, and we can see how everything above this plane is going to be cis to one another. So all of these red dots are cis to one another. Now we can go through, and let's get another color for this. We'll do orange. And we can look at the bottom side. Now, right here, we'll start with this bottom one. That's below this plane. And this one right here, this is an equatorial below the plane. This one right here is axial and below the plane. So it's also cis. And actually, just to make sure that we can see this, I'm gonna do it in a different color. I'll do it in green. So remember, we have this equatorial right here, which is on the bottom side of this plane. This axial, which is on the bottom side of this plane, and those are cis to one another. So we can go around. This is an equatorial. This is an axial. Equatorial, axial. And these are all on the bottom side of this invisible plane. So here, all the red are cis to one another, and all the green are cis to one another. So what we can do is, if we're looking at this red and this red, they're cis. But this red and this green are trans. So these are trans on the opposite side of this invisible plane to each other. This one's above this plane, and this one is below this plane. So those are trans to one another. So this is how we can look at cis-trans configurations when we're looking at different chair constructions. So if we were to go across and we were to look at trans, it would be trans axial, 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 axial. Those are all trans to one another as we move around the carbon. Same thing with equatorial. If we're looking at trans, it goes equatorial is trans to this equatorial. This equatorial is trans to this equatorial, and so forth, as we go around the molecule. So that is how we can look at cis and trans. So now that we understand how to draw the axial and equatorial, why they are cis or trans to one another, we're going to look at chair flipping or chair conformation. So I'm going to redraw this. So we're going to start with this chair in this particular conformation. All right. So again, we're going to go through and we're going to label all our axial and equatorial. Oops. Sorry about that. Equatorial, we're going to go in green. Okay. So now what we're going to imagine is we're going to create this chair conformation over here. And what's going to happen? All right. So here's what we've done. Imagine that these two carbons right here are set, all right, and there's a line in between it. And what we've done is we've taken this tip right here and we've brought it down. Okay? So this carbon right here is the same as this carbon right here. And on this side, we did the same thing. We're keeping generally these carbons the same. But we went ahead and we are flipping this up now. So that's going into the up position. Again, this carbon right here is the same as this carbon here. But now let's pay attention to what happened to our axial and equatorial positions. This is what's quite interesting. So if we look at this one right here, A, all right, and actually, before we do this, let's go ahead and label all of our axial and equatorials on the other side. So, or actually, let's not do that. We'll come back to that in a second. So what's going to happen is we have A in this axial position, and when we flip it down, all right, this green equatorial position is going to go down, and it's going to go to the axial position. But this original axial A is going to go flipping down, and it's going to go into the equatorial. So what we're going to have now is we're going to have A be in this equatorial position here. All right? And let's say if this were B. Well, now, B is facing downward, and it's in the axial position. So what does this mean? So let's look over here on this side of the molecule. Let's label this C. We'll label this D. All right. So what happens is when we flip, again, we're flipping this up. Well, D, which is here, now goes into the axial position, and C goes into the equatorial position. So we have C right there. We have D that's flipping up into the axial. So we have C and we have D. Those are flipping now. So what's happening is as we change from these two chair conformations, all axials are going to switch into the equatorial position, and all equatorial are going to switch into the axial position. So all the green over here, we're in the equatorial position, but now, once we do the chair flip, they're going to switch to the axial position. All right? And all of the equatorial or axials that were over here are now going to switch into the equatorial when you do the chair flip. Okay? So no matter what happens, when you do a chair flip, all axials go to equatorial and all equatorial go to axial positions. So this describes generally what's happening with the chair. We've now explained how we got to the chair conformation, how to draw the axial and equatorial positions, and then also what happens when we do a chair flip. The last thing I want to talk about, and I'll do an example real quick. And this is an example on the recitation packet, or similar to that example, but I want to do it for you just so we can explain why things want to be in the equatorial axial position. So let's say, all right, let's say we had in this position here, remember wedges are coming out of the board, we have a isopropyl, all right? And over here, also going into the board, we have a methyl. So again, isopropyl is just the CH, CH3, CH3. It's a kind of, it's a little bit of a large and bulky group, and the methyl is just a CH3 group. Remember, Alkyls are not functional groups, they're just constituents, so don't label them as functional groups. But these are our constituents. We have the isopropyl coming out of the board, and we have the methyl coming out of the board. So let's go ahead and label this. Let's see, methyl, we'll label this 1,4, okay, as carbon 1 and carbon 4. So let's convert this structure here into a chair structure. So first, go ahead and draw your chair, and also label your, go through and just put all of the axial and equatorial tick marks. Okay, so we went through, let's make sure it's pointing up, both pointing down, pointing up, pointing down. Yep, we went through and labeled our axial and equatorial tick marks. So it does not matter which one you start with first. So let's start with isopropyl, and let's just say, let's erase this now that we know what isopropyl is, and let's just say we put it on this axial thing here. So we'll call this carbon 4, and if we follow our carbons, we have 1, 2, 3, 4, so we're 4, 3, 2, 1, so this is your carbon 1. So on your carbon 4, we're going to place the isopropyl group in the axial position, okay? So if we want methyl to be on the same side, again, these are both coming out of the page, so they're both cis to one another. We're going to go to this one position, and we notice that the isopropyl, again, imagining that imaginary plane is on the lower side of that plane. Well, in the one position, the lower side is this equatorial, so we're going to place the methyl group right here, okay? So now we can go ahead, and we've correctly labeled, again, on all these other ones we have just protons, or hydrogens, I'm sorry, going across the entire board. Okay. And now we can do a chair flip. Right? So now when we do our chair flip, isopropyl was originally in an axial position, but now it's in equatorial. And this is our 4 carbon here, right? Our 1 carbon has now, remember, our 4 has flipped up, and our 1 carbon has flipped down, and our methyl carbon, again, we were originally in the equatorial position, but now we're going to go into the axial because we flipped the chair. Okay? Now, I could draw on all the other ones, but we don't need to understand what's happening. So now we have isopropyl in the equatorial position. So if we were to look at these two, what we would say is this conformation right here is more stable. And here's why. If we go back and we look at this original one here, remember, isopropyl is a big bulky group. And what's going to happen is it's going to have steric interactions or interference with this hydrogen here facing down and this hydrogen here. So it's going to be interacting with those, and it's going to be like, all right, I don't really like interacting with you. I'd rather be in this equatorial position where I'm as far away from other constituents as possible. So we have isopropyl in the equatorial position, but we put methyl in the axial. Now, methyl will still be interacting with these hydrogens in the same way, but methyl is less bulky, it's less big, so it's not going to have as much steric hindrance as the isopropyl group did. And that is why we want to put isopropyl into the equatorial position and why we want to have methyl in the axial. Remember, isopropyl larger, has more steric hindrance with these protons here on the bottom side, and so therefore we prefer to be in the equatorial position, which is further away from the rest of the mess of the cyclohexane. So this hopefully helped explain chair conformations for everyone in the class. If there are any questions, again, please do not hesitate to either email me, Allison, or Dr. Pillay. So I hope you all have a great weekend, and I will see you on Tuesday for the test.